This is lecture 4 for magnetic fields. This again comes from chapter 29 in your text. We are looking at magnetic fields produced by current carrying wires. Let's start today with the magnetic force between two current carrying wires. Okay, so for example, suppose I have one wire with current I1 going in this direction, and I have another wire with current I2 also going in a parallel direction. And let's say they're separated by some distance, we'll call it A. Well, from what we know before, let's look at the force on wire 2. If wire 2 on wire 1, wire 1 has a current of I2, that will set up a magnetic field at wire I1. That being the case, if I use the right-hand rule, I've got the current in I1 going this way. The magnetic field that's created by wire I2 is coming out of the board at wire I1. So if I have the charges going this way, the field coming out of the board, the force on wire I1 is going to be towards wire I2. By the same token, the current in wire I1 is causing a magnetic field that's going into the board at wire I2. So I have a magnetic field going into the board down here. I have a current that's going, a charge is moving from left to right. Therefore, I have a force that's going upwards towards I1. So one of the things that we learn immediately, just qualitatively, is that if I have two current carrying wires where the current is in the same direction, they're going to be attracted to one another. So the force will be attracted between the two wires. On the other hand, if the current of one wire is going opposite the current of the other, then of course it would be repulsive by the same argument. Let's do a little calculation though. Suppose I want to find the force on wire 1 due to wire 2. Well, the force on wire 1, we have said will be IL times B, since everything's perpendicular and parallel. This would be the current of I1 times the length of I1 times the magnetic field due to wire 2. The magnetic field due to wire 2 would be mu naught times I over 2 pi A by Biot sub R law. Therefore, the force would be mu naught I1 I2 divided by 2 pi A times the length, which means that the force per unit length of wire would just be mu naught times the product of the currents divided by 2 pi A. One of the things that we can do is, in fact, define the ampere by this experiment right here. And this is the way we would do it. If I have two long parallel wires, separated by 1 meter, if the force per unit length of one wire on the other is 2 times 10 to the minus 7 newtons per meter, and they carry the same current, that current is equal to 1 ampere, or 1 amp. So that's how we define the ampere. Two long parallel wires, they're separated by a meter, and if the force per unit length is 2 times 10 to the minus 7 newtons per meter, the current is defined as 1 amp. That's how we define the unit of current. Surprisingly, we use this definition to define the unit of charge, the Coulomb. Coulomb, that says a wire carrying a steady current of 1 amp of charge flowing through a cross section of conductor in 1 second that amount of charge is 1 Coulomb. Completely the opposite of what you might think, because we started with electrostatics in this class, we defined the Coulomb very early on, but in reality, it was the definition of the amp that enabled us to define the Coulomb. Kind of interesting. That being the case, now I'd like to talk about a really fundamental law in magnetostatics, and it's one of, as it turns out, it is a part of one of the 4 important Maxwell equations of electromagnetism. That is Ampere's law. We're going to cover the unmodified version of Ampere's law, Maxwell modified Ampere's law. We'll talk about that later on in the course. But for now, we're going to use the unmodified version of Ampere's law in this way. So one of the things we know, if I have a current carrying wire, I can find if the current is going from your left to your right. The magnetic field then, if I use my thumb to indicate the direction of current, the magnetic field is going to wrap around the wire like so. And the field line is going to form concentric circles around the wire. If I look at the blackboard, the field comes out of the board over the top, goes into the board at the bottom of the wire, such that we have concentric circles. Moreover, if we vary the current and the distance from the wire, we find that the magnetic fields are proportional to the current and 1 over the distance from the wire. So what we're going to do is evaluate the term B dot ds and sum the products over closed circular path centered on the wire. So I'm going to draw this path around the wire. I'm going to call it ds, around the wire. And I notice that, of course, everywhere around the wire, ds and B are parallel to each other, which is to say that then B dot ds I can just write as B times ds. Magnetic field then is constant everywhere on this loop that I draw around the wire. And that's going to be crucial. This will remind you of kind of the way we operated when we did Gauss's law. So in this case, I can say the integral of B dot ds around the wire is equal to B times the integral. The field is going to be constant everywhere on B. Integral of ds is equal to mu naught I over 2 pi r, which is the magnetic field for a wire, times the integral of ds, which is just the circumference of the loop around the wire. In other words, what Ampere's law is trying to tell us is that the integral of B dot ds around the wire is equal to mu naught times I. And this is what we call Ampere's law. The line integral of B dot ds around any closed path is going to be proportional to the current that goes through that path. It's valid always, but it's extremely useful for calculating magnetic fields where you have high symmetry. And that's what we're going to do. We're going to show you some examples of magnetic fields that come from configurations, current configurations of high symmetry. We'll branch out from there, still highly symmetric, but we'll use some non-uniform currents as well. This procedure will remind you a great deal of what we did with Gauss's law. So let's do the first example. Let's do suppose I have a current carrying wire with a constant current I naught going through the wire. Let's say the wire has a radius of capital R, and I want to find the magnetic field at some point inside the wire and then some point outside the wire. Okay? Let's start with the easy one. Let's do it for R, little r greater than R. So I'm at a point outside the wire. Suppose I want to calculate the magnetic field. That's at this point. What I'm going to, so I'll put this point here. What I'm going to do is I'm going to draw not a Gaussian surface, but an Amperian loop around the wire, and we'll have a radius of little r, like so. And then I can employ Ampere's law and say the integral of B dot ds is equal to mu naught times I. In this case, the current is constant. It's I naught, so it's mu naught times I naught. My Amperian loop is covering all of the current. So all of the current in that wire is passing through this Amperian loop. So I'm covering all of it like this. ds is this loop, this line element around the loop. That's just going to be equal to 2 pi r. B and ds, by the way, are parallel to one another, so this becomes B times ds. B is constant, so I can pull it outside of the integral. And then the integral of ds is just the circumference of that loop, which is 2 pi times little r. Therefore, the magnetic field at that point outside the wire, of course, as I would expect, is mu naught I naught times 2 pi r. And you could get there using Gauss's law, but it's a much more involved process. This is a very simple process. Okay, it's a uniform current carrying wire. Now I want to find the magnetic field inside the wire. To do that, let's say we have a point in here, some distance r from the center. I'm going to draw a small Amperian loop, but the issue here is that I don't have all of the current in the wire passing through this loop. I only have some of the current. If it's a uniform current distribution, I can say, though, that the current density, J, is equal to the current divided by the area of the loop. So I can say then that the current that's going through, the total current through the wire divided by the area of the cross-sectional area of the wire, which is pi capital R squared, has got to be equal to what I'll call the effective current. That's just this current that's sliding through this loop, divided by pi times little r squared, right? Current density is always current per unit area. So I can find my effective current as, and it's going to be I naught little r squared over capital R squared. I can take my answer now and put this inside Ampere's law. Once again, B times, B's constant everywhere on that loop. ds is just 2 pi r, where r is the radius inside the wire, is going to be equal to mu naught times I naught r squared over capital R squared, and therefore the magnetic field inside the wire would be mu naught I naught little r over 2 pi capital R squared. It's a very nice example of how to use Ampere's law in that way. Notice, if I were to plot the magnetic field as a function of r, the field goes as r is proportional to r when I'm inside the loop, when I'm inside the wire, but it goes as 1 over r when I'm outside the loop. So it's a nice little illustration of what happens with the magnetic field. That's it. We'll do non-uniform charge current distributions in the next lecture.